Welcome to Excel 2013 Statistical Analysis video number 20. If you want to download this workbook and follow along, click on the link below the video. Hey, we got a great video here. We got to talk about variability or dispersion, and more specifically about standard deviation. Now, here's two data sets. Number of hours worked per week, job number one. Number of hours worked per week, job number two. And check this out. The average for this job is 35. That means an average of 35 hours worked per week. And this one's also 35 hours per week. Now let's look at this here. I plotted. Here's the hours. And guess what? That right there is the average hours worked for job number one. That's plotted along this axis. So that point right there just means 35, right? Oh, but this job two, the mean right there, is exactly the same. Now check this out. Here's all the data points for job number two. Notice when I plot them, there's a 43-hour, a 36-hour, a 30-hour. So those are all the data points, and this is the mean. Remember, the mean is a single value that represents its data points, a measure of central location. Well, what about this one? Well, it's 35, but notice that the actual data points, and this one is 15, this one is 59. They're much more spread out. So what does that mean? Well, if you say the average hours worked per week is 35 for both jobs, you're like, oh, they're the same. No, they're not the same. Until you look at the spread or the dispersion, you don't really know if they're the same or not. So one question that standard deviation can answer is, which mean more fairly represents its data points? Right now, this one, because all of these values are much closer to that. Now look, the distance between these two and this one, that little distance there is called a deviation. It means here's a particular x, here's the mean. How far are they apart? This one is going to be a positive. This one's going to be a negative, meaning it's below the mean. Down here, it looks like the deviations are much larger, right? So this is just a visual portrayal, trying to get our arms around what dispersion or variability or eventually our standard deviation means. Let's go look at another example. So on V2, we have gas prices from Burien, and we calculated an average, and gas prices from Seattle, and we calculated an average. Now, these are not exactly the same, but we might ask the question, where are prices more volatile? Again, that's going to have to do with the dispersion or spread in the data points. Here's the mean for Seattle. There's the spread in the data points. Here's the mean for Burien. Here's the spread in the data points. We want to find a measure that will tell us, a single number that will tell us which data set has more volatility. Let's go look at another example on V3. Here are days to fill an order. So we run a company, and we order specialized wood from Banderson and from Plywood and Floor. Now look, the average time for them to deliver to us our wood, our custom wood, is 9 days at Banderson's and 9 days at Plywood and Floor. So they're both the same? No, they're not. Check this out. Here is Banderson's, exactly 9 days on average to get our order. But look at the spread in the data. Down here, this is Plywood and Floor. The spread is much larger. Now, we might be happy when we get our order in 4 days, but on this day out here, this is 16 days it took for them to deliver our order. So the spread in the data is much greater here. That 16 might really negatively impact our business. So if we had a measure to measure the variability or the dispersion for our two suppliers, the one with the smallest amount of variation might be a more reliable supplier. So the question standard deviation is going to answer here is based on average days to fill the order, which supplier is more reliable. Now let's go over to the sheet V5, and we're going to talk about a few different ways to measure variability. The easiest is the range. You simply take the max and the min. The nice thing about range is it's simple to calculate. The downside is it's very sensitive to the small and largest values, the extreme values. We're in essence only calculating from two numbers in the data set. But still, it's a useful calculation. We want to see the range, so I'm going to take the max. And this is a relative cell reference. I'm highlighting Banderson's, Control-Enter. And now I copy it over. So there's a max for both. You could put it in edit mode and check to see that it got it right. Equals the min for the smallest, relative cell reference. Control-Enter. The min is 4. Ooh. The min is 6. And the range equals the largest minus the smallest. Control-Enter and copy it over. So there's a range of 12 days and 5. In our example here, that doesn't sound very good if we're trying to plan our business. A range of 12 days compared to a range of 5. I kind of like the 5 better. Another way to calculate dispersion or variability is the interquartile range. You take the quartile 3 and subtract quartile 1. This will give the range for the middle 50% of the data. It overcomes the sensitivity to the extreme values that range suffers from. Hey, let's go ahead and calculate quartile.exe. I'm highlighting Banderson's, comma. And now I'm going to get that 1, F4 to lock it. Control-Enter. And now I'm going to copy it over. Notice one of them was relative and one of them was absolute. The blue one moved over to the side, but the one remained locked down. Now quartile 3 equals Q. It's the first Q function tab. Relative cell reference. We have Banderson, comma, and I'm going to get that 3, F4, Control-Enter, and copy it over. So we have quartile 1 and 3 for both of our suppliers. Now we can calculate the quartile range. The third, that means the biggest, minus the smallest of these two. Quartile 3 minus quartile 1, Control-Enter, we have 6, and we have 2. So the middle 50% of the data points, we have an interquartile range of 6 and 2. Now, really what we'd like is we'd like to have a measure that uses all the values. So we want to go over and talk about standard deviation. We want to click on V6. Here are our formulas. Population variance and population standard deviation. We're using sigma, the Greek letter, to represent variance for the population. The only difference between these two things is we take the square root here. So sigma squared is variance for the population. Sigma is population standard deviation. Now, most of the time, we're going to be doing sample variance and sample standard deviation. In fact, we're almost always going to be doing just this one, sample standard deviation. The only difference between these is that to go from variance to standard deviation, we take the square root. And we'll talk about this. This is a pretty amazing calculation. Let's go over to V7. Now, a deviation, it is how far one datum is from the mean. It just means our particular value, how far is it from the mean. So for each one of the sample points, we're going to calculate that deviation. Is it below the mean or above the mean? Then sample standard deviation will give us a numerical measure that says how much variability there is in the data points. You can think of standard deviation as an average of all of the deviations. And as we do our step-by-step calculation, we'll see that that's exactly what we're doing. Standard deviation will tell us how fairly the mean represents its data points. Because remember, it's going to be measuring that spread in the data. The bigger the spread, the less fairly the mean represents its data points. The more clustered all the points are together right by the mean, the more fairly the mean will represent its data points. And again, standard deviation will tell us how clustered the data points are around the mean. Hey, let's scroll down here. I have this Banderson and plywood and floor data. Notice these are more clustered around the mean. These ones are more spread out. That's what standard deviation is going to help us measure. Now, the first thing is here's our data set. All right, so here's Banderson's. Here's plywood and floor. All right, so ready? We're going to count first because we're going to need that. And we're counting numbers, so I'm going to use the count function. And there's our count and enter. Now, count minus 1. We're going to need that in our calculation. So I'm going to say, hey, 15 minus 1 and enter. X bar is going to be average. And we will highlight Banderson's. We already know what the answer is. It's 9. Now notice those are all relative cell references, so I can copy all of those formulas and paste them right here. And sure enough, absolutely perfect. Now here's the deviation, right? These are the particular values. So on one occasion, they delivered in 4 days. Another occasion, 6. Another, it took 12 days to deliver. So if we take a deviation equals the particular x minus our mean, and I'm going to hit the F4 key to lock that. That's our deviation. Control Enter, and now we copy this down. I'm not going to double click because I have that total there. Now here's the strange thing about deviation. Alt equals, we would like to add them all up and divide by the count, or n minus 1, to get like an average deviation. But here's the problem. Enter. All of the deviations, every time you add them up, it's always equal to 0. And you can look down here. These two right here, above, these two below, there's a bunch below and above. Every time you add up those deviations, it's always equal to 0. So here's what they did. And there's not just one way to do measures for variation. There's other methods too. But the one that's most common is going to be, we're going to square it, because the square of minus 3 will give us 9. The square of 3 will give us 9. By squaring, we kind of are getting all the positive numbers, so we can add them up and divide by the count. Now the cool thing is, notice we're squaring it here. At the very end, we'll undo that square by taking the square root. So you ready? Equals the deviation, Shift 6 to get that caret, 2, Control Enter, and I'm just going to click and drag. And now when I add all these up, Alt equals, that's the sum of the deviation squared. That's this top part of our formula. So Enter. Now we simply have to take the top part of our formula, which is 192, and divide by n minus 1. There's our n minus 1. Now why n minus 1? I have a little note up here. Sample data divided by just the count tends to underestimate. And so by subtracting 1, it adjusts it so that it's a little bit more accurate. You can think of it this way. If we had 10 divided by 5, you know that equals 2. But if we subtracted 1, notice that by changing the denominator and making it a little bit smaller, it makes the whole result a little bit bigger. And so since sample data divided by just the count underestimates, by subtracting 1, it tends to push it up just enough to make it a little bit more accurate. Now that is sample variance. The problem with sample variance is that the units are squared. As soon as you have any number and there's a unit and you square it, the units get squared also. So what do we do to calculate our sample standard deviation? We take the square root, in essence undoing this square we did up here to deal with the fact that they all added up to 0. So we're undoing it at the end, and boom, that is our sample standard deviation. So for Banderson's, remember the units are days. The average time to deliver the custom wood order for Banderson is 9 days, with a sample standard deviation of 3.61 days. So that's for Banderson. As soon as we calculate for plywood and floor over here, obviously the standard deviation, which is the smallest, meaning the average deviation time, number of days, the smaller one's going to be better for us in trying to run our business. Now we did this longhand so we could see that the deviations add up to 0, that we had to do something because that's true, and so we squared it. We then divided by the count. We had squared units, so we took the square root to undo that. So it's good to do all of that and see how it's calculating. But once you get the hang of it, we will just use equals variance, and there's a P for population and an S for sample. I'm simply going to highlight, and it will do all the heavy lifting. Boom. STDEV, and there's a P and an S. We're going to use the S. Highlight all of Banderson's, and boom, 3.61 days. Now doing this again by hand doesn't take too long. I'm going to say, hey, the particular value for plywood and floor minus the mean, F4, Control Enter, copy it down. So these are all the deviations, right? We add them all up. We're hoping that we get some number. No, that's always the case. When you add up the deviation, it's going to be 0. So we got to do something. We're going to square it. Control Enter and copy it down. Now I need to add up all the deviations squared. So I Alt equals, and boom, that's the numerator. Now I can divide that amount there by the count minus 1. And there is the variance. But now I really want the standard deviation. So square root. And boom, there it is. 1.2 days is the standard deviation. The average deviation time for plywood and floor. For Banderson, it's 3.61. So we like the 1.2 better. And of course, we can do our variance for the sample. Enter, enter. And our standard deviation, STDEV.S. And we highlight, and we get 1.2. Now, these are sample statistics. Our sample standard deviation. S is a point estimator of the population standard deviation sigma. Now, which mean more fairly represents its data points? Remember, they were both 9. Well, clearly, this standard deviation is much smaller than this one. So this 9, since it's standing in one value representing all the data points, more fairly represents its data point than this 9 mean calculation does of its data points. Now, let's scroll down. We want to look at a few more examples. Hey, there is that chart. There's a histogram even. You can absolutely see the spread in the data using histograms. Now, they mention this in the book. You do not have to do this. There's an alternative calculation. And if you were good at doing transformations in algebra, you could actually prove that this formula and this formula up here are exactly the same. It's there if you want to see. We don't have to do it. We're going to basically use the STDEV function. There's also other ways. So instead of squaring, well, you could take the absolute value of each one of these and then divide by the count. It gives you a slightly different number, but sometimes people use that to measure dispersion. Now, we want to come down here. Here are our hours per week for each one of these. So let's go ahead and calculate. We clearly see from our visual portrayal here that the mean from job number 2 more fairly represents its data points. But let's get our measure equals STDEV.S. Relative cell references. Control Enter. And copy it over. So see here we have an average of 35 hours worked per week. But for this job, look at that. 17.8 hours of standard deviation. That means the average deviation was about 17. Here, the average deviation was about 3. So 35 more fairly represents its data points. With our measure, standard deviation, or our visual over here. Here's our gas prices example. We have an average gas price in Burien, an average gas price in Seattle. Which one has more volatility? Well, it's kind of hard to tell from this chart here, but we can certainly use our measure, STDEV.S. And I'm simply going to highlight the gas prices from our sample from Burien. Control Enter. It's a relative cell reference. So it looks like $2.56 with a standard deviation of about 30 cents. I'm going to drag this over. Ooh, this one's 47. I'm going to add some number formatting. Control-Shift-4 for currency. So here we have a mean with a standard deviation. Average gas price in Burien is $2.56 with a sample standard deviation of 30 cents. $2.66 for Seattle with a standard deviation of 47 pennies for Seattle. Clearly, there is less volatility in Burien, more volatility from our sample data in Seattle. Now we have another important topic we want to talk to. We want to go over to V9. We want to talk about coefficient of variation. The formula is simple. We're going to take our standard deviation divided by our mean. Now, why in the world would we do that? Sometimes data is in different units or data is in the same units, but the means are far apart. And so we want a relative measure. So if we take each one of the means and standard deviation and make this calculation, it will give us coefficient of variation, which will tell us for every 1 unit of mean what is the standard deviation. And then we can use those numbers to compare. Now, first example, we want to compare mean bonus paid per employee and the mean number of years worked at the firm. Well, look at these. The standard deviation here is $755 compared to 3 years. You just can't compare those. They're different units, but no problem. We can express each one of the standard deviations in units of x bar. So I'm simply going to say, hey, $755. That's the standard deviation for bonus, and I'm going to divide it by the mean bonus amount, 2,000. I get 38%. Now, one thing that's nice about this coefficient of variance is the actual units cancel out here, so we're left with just a percentage, right? However, in order to understand what this really means, I always like to do this trick. And this trick is great for any ratio where you have units. I just went ahead and wrote it out with all the units and everything. So in the numerator, we had $750 of standard deviation for the bonus, and denominator had $2,000 a mean for that bonus. But when we do the calculation, instead of just writing it as 38%, which is what we want to use here, but for trying to understand it, keep the units up here. It means I got 38 cents of standard deviation for every $1 of mean. So by doing this, we get a relative measure. We're left here, since the units cancel out in our calculation, 38%. Now we simply come over here with our years. 3 years standard deviation divided by 15 years. The years cancel out. We're left with 20%. So a relative measure. There's clearly more variation or dispersion in the distribution for bonuses paid. Now that's one reason you'd want to use coefficient of variance. Another one is when the means are far apart. So we have wage sample data from city 1 and city 2. Let's go ahead and calculate the average. Highlight the range. And enter. And then the standard deviation. All right, so for this city, we have, and from our sample, we have $22.64 as our average wage with a standard deviation of $10. What about over here? We have, boom, a mean of $37.95 and a standard deviation of $28.58. So we can't really directly compare these. The means are far apart. No problem. We have coefficient of variance equals standard deviation divided by our mean. I come over here, so we get a relative measure of variance of 47%. And then over here, standard deviation per unit of mean, boom, 75%. So clearly, the variation and dispersion in data points in wage data for city 2 much greater than for city 1. So covariance, great when you have means that are far apart and you're making comparison, or actual units that are completely different. Now, 2 more topics I want to scroll over. I want to go to the sheet DS. Now, here is a data set we used last chapter when we were building histograms. I'd like to use data ribbon over in Analyze and data analysis to get to the descriptive statistics feature, which will quickly calculate a bunch of measures for us. So I'm going to go ahead and do it. Data, analysis group, data analysis. And there it is, descriptive statistics. And click OK. It's going to ask where the column is. We want to analyze revenue. Control-Shift down arrow. The data is in columns. There's a label in the first row. My output range, I'm going to say, hey, put it in N3. And now we come down here, and I'm going to say summary statistics. We could even ask for the kth largest. So if I said second, it would give me the second largest. We'll talk about this one later in the chapter on confidence intervals. I click OK, and instantly, look at that. It calculated the mean. Standard error, we'll learn about that later. Median, mode, standard deviation, variance, skewness, range, max, min, sum, count, and even the largest two. However, this data is not linked. It is static. So if the data were to change, you'd have to run this feature again. Now, our last topic, I want to go all the way back to V4. And I want to show you how to create this chart right here. This is not required for the class. Don't have to do it on a test or anything, but I do want to show you how to do it. We're going to use the XY scatter, and we have to kind of get creative because, look, this really doesn't look like an XY scatter, mostly because I took away the vertical axis to show us the number, because these numbers are really irrelevant, meaning the height here. I'm just lining them up in a line. But I do want to use an XY scatter, and here's how we're going to do it. All of these x values, boom, 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 they all have to have the same y. It's going to be like 0.5. This one will be the mean. It will be a single plotted point at exactly the mean, and then we'll give it about 0.75. This will be about 1.2 for the y, and this will be maybe a little bit bigger. So let's go over and see how to do this. The trick is I'm going to just pick. I want Banderson on the bottom, so I'm going to highlight. And I'm going to put a number here, 0.5. And now I want to populate that number all the way through the highlighted cells, so I use Control and Enter. That actually is a cool trick. You could put whatever you want, a formula into all the cells or whatever. Here, we're going to highlight and put 1. And we can adjust these numbers later if we don't like the way the chart looks. Control Enter. I love that. This one will be right above this, so I'm going to put 0.75, and this one will be 1.25. All right, so this is an x and a y, x and a y. So I'm first going to highlight and go up and get my scatter chart. Insert, chart group, drop down, and boom, look at that. So we can instantly see that it did work. Now I want to add some more series data. That means the numbers. I want to move this out of the way because I'm going to have to access the data here. So now I go up to Design, and there it is in the data group, Select Data. And this really is the power of charting, because now we're not limited to clicking the button and having the data go where Excel thinks it should go. We can put our chart together any way we want. So I'm going to click Add. The series name, days to fill order for plywood and floor, the x values. And then right here, there's equals, curly bracket 1, curly bracket. That is going to get in the way, so you want to be sure to highlight it and delete. You got to delete it before you go and get the values over here. So I've highlighted my y values. Click OK. Just to show you, click OK. So now it's starting to look good. Design, select data. And now we want to add, but watch this. I'm going to say mean days for supplier 1. X is going to be a single point. And again, this y, I'm going to have to delete that and then get that 0.75. Click OK. I'm going to add again. Series name, mean days for supplier 2. X, highlight, delete, and let's get our y. And OK, and then OK. And there, it's looking good. Now, we actually don't need this. I'm going to delete it. I don't really want any of these lines. I see the dots on either side, so I delete. Oh, I don't want to delete that. I want to actually delete the vertical grid lines. Delete. I definitely need a label on the bottom. Click the plus. Axis title. I'm going to hit delete because that one's highlighted. I'm going to click on this one and type. Days to fill order, and enter. Now I want a legend, so I'm going to go up to the plus and say, give me a legend. I'm going to click on the legend, either right-click Format Legend or Control-1, and I'm going to put it at the top. And there is a chart that shows us the dispersion or variation or spread of the data. All right, in this video, we talked about dispersion and spread in the data. We saw visually this chart. We also learned about the range and the interquartile range. We then learned about the very important and often used variation, but standard deviation for the sample. We did it longhand. We also saw that there's built-in functions like STDEV. We saw that there is a way to compare relative variability with coefficient of variance. And we even saw on descriptive statistics how to quickly calculate a bunch of numerical measures using data analysis, descriptive statistics. All right, next video we'll talk about skew. All right, see you next video.